All right, let's take a look at numbers 14 through 16. And actually, I just went through all three of these problems, but I had the camera on camera mode, not video camera. So, well, it should at least be fresh in my memory here. 14 through 16 all go together. These are the gravity problems that we've seen before. So we've got Titan, one of Saturn's moons, that we're going to be studying here a little bit. And we know the mass of Titan, and we know the radius of Titan. So let's start off by finding Titan's surface gravity. And so what this is, we usually use this symbol lowercase g here. So on Earth, it's 9.8 meters per second squared. And that's called Earth's surface gravity, the rate at which objects accelerate towards Earth when we release them. And so we're going to find the same thing on Titan. Objects may not accelerate downwards towards Titan's surface at the same rate as on Earth. They won't. So what are we going to do? Well, we're going to derive the result that we're going to plug into. And the way we're going to derive the result is we're going to say that if we have, let's put Titan here. So here's Titan, and let's just say that its mass, let's call it big M, and we know what big M is. Let's say that we also know the radius of Titan, that's also given here. And we're going to consider another object that is on the scale of Titan. It's going to be pretty small, so maybe we can consider, hey, we're dropping an object near Titan's surface there. And let's say that it has mass little m. Now, the way we're going to get a result is we're going to look at our force of gravity. What do we know about the force of gravity? Here, when the object is released near Titan's surface, we know that the force of gravity, it's perfectly fine to write it as the mass of the object times this surface gravity that we're trying to find. We also know, this equation appears valid for any objects on or near Titan's surface. We also know that Newton's universal law of gravitation should be true, because it's always valid for any 2 point particles. So we have to make a little argument here. And that looks something like this, and maybe I'll just write the formula for now. We usually, in general, we would see something like that in the formula sheet. So what we're going to do is say, hey, these both must be correct, so we're going to equate them. And so that's going to look something like this. We've got our mg. I'll rewrite that here. And that must be equal to this. Now, this equation is only valid for point particles. However, if we have a spherically symmetric object, which we're going to consider Titan to be, then we can make an equivalent problem. Mathematically, it's totally equivalent if we want to calculate the force here, or the potential energy in our next problem. That we can say, hey, we can leave the small object here. I'm just going to draw it directly below. And we can say, hey, I can take all of Titan's mass and concentrate it at its center. So I'm going to draw that right below the center. And there is all of Titan's mass. This is an equivalent mathematical problem. And we can see that in this equivalent problem, that distance, the distance between the two objects, should be the radius of Titan. Now we can plug in here. We've got the universal gravitational constant. We can look that number up. We've got the mass of our object, the mass of Titan, and the distance between these two particles squared. And so this gives us the result, the mass of the object that we're considering here. That mass cancels out. And this gives us the result to calculate surface gravity. Our value of, this is a gravitational constant, the mass of Titan and the radius of Titan squared. And when we plug those in, I'll leave the calculation to you here. We'll get 1.35 meters per second squared. All right, let's move on to number 15 here. Find Titan's escape speed. And I'm going to redraw my picture. Okay, get some room here. Escape speed. And escape speed, our definition is that if we have Titan here with the same mass and radius, if we fire some rocket or bullet or something, we fire it directly away from us, the escape speed is the minimum speed needed so that this rocket or bullet is going to move away from Titan. And as it's moving away, it's going to slow down because Titan's gravity is pulling on it. but the minimum speed needed so that it never falls back down. Now, if it never falls back down, what that means is it's going to keep moving this way, and it's going to slow down, slow down, slow down. And so the final situation we'll have is that the rocket or bullet or whatever is very, very far away, and its speed is close to zero, approaching zero. So we're going to need to use that information. Now, we're going to solve this by thinking about our work energy strategy. And so with our work energy strategy, I like to label the initial situation and the final situation. The final situation is infinitely far away, so I'm not going to draw that. But we know that the rocket's speed goes to zero, and it's very, very far away. Now, we also talk about where the potential energy, we have to choose where the potential energy is zero, or what we did before, we choose the height where the height is zero. Now, when we want to use if we look up our gravitational potential energy equation, it's going to look something like this. And there's just one r here, the distance between the two objects. Given that this formula, we do not get to choose where the potential energy is zero for the two objects. It's chosen for us. The potential energy we can see will approach zero as this distance between these two objects approaches infinity. So that's chosen for us. Finally, we should think about the work done by non-conservative forces. All right, if we're applying our full work energy strategy, and well, as the rocket moves away, the only force that we're considering to be on the rocket is gravity, which is a conservative force. And so this is going to turn out to be zero. And so now we can go ahead and use our work energy equation. That looks like this. And we already saw that the non-conservative forces don't do any work, and so we have what we call conservation of mechanical energy. The total initial mechanical energy equals the total final mechanical energy. Now I'll tell you what, let's think about these final terms first, because I think that's going to be a little bit easier for us. And again, in the final case, as it gets really far away, its speed approaches zero, the final kinetic energy also approaches zero. Additionally, the final gravitational potential energy. In the final case, it's very, very far away, which we're considering the distance to go to infinity, and in that case, the final gravitational potential energy also approaches zero. So it's a little interesting over here that the total energy is zero. How can that be the case? Well, on this side, I do expect kinetic energy 1/2 mv squared. That's non-negative. It can't be negative. But on the other hand, our gravitational potential energy can't be positive, so it seems like this equation can work out. So let's plug in here. The initial kinetic energy. This is going to be 1/2 mv squared. And let's think about this. This is the mass. I better specify on here. This is the mass of my rocket here, little m, mass of Titan, radius of Titan. So this is the mass of our rocket. Now it's v. We've plugged in information about calculating the escape speed, and so what we are calculating, in fact, is this. It's not any speed, it's the escape speed here. That's what we're trying to find. And now we can add in our initial gravitational potential energy. And so we're just going to follow along this form, and we're going to have our universal gravitational constant, multiply the two masses. And initially, what is the distance between the two objects? What is the distance? Again, we're going to consider, it's very close to the surface, but the distance isn't zero. We do an equivalent problem. We take all of Titan's mass, focus it at the center. And so the initial distance between these two objects is the radius of Titan. And so we can see that we can divide through by the rocket's mass, and we can get the result for the escape speed. And so all this stuff we know here. The universal gravitational constant, we can look that up. The mass of Titan and the radius of Titan. And when we plug those numbers in, I'll leave that up to you, we get answer D here. And so let's finish it off with number 16. I'm going to clear myself some space here. And on number 16, the question is not completely clear. It just says that there's a satellite that orbits at this distance. We do need to consider it to be moving in a circular orbit of this radius. And so if I'm going to, once again, I'll draw in Titan, and let me just give it the same mass and the same radius here. And let me draw the trajectory of our satellite. It's going to be, we're considering it to be a circular trajectory here. And let's look at, what we're going to do we're going to start off, we want to find the period, the orbital period. How many seconds it takes to complete one cycle of the orbit here. And the way we're going to do it is we're going to start off by using Newton's second law. So let's consider our satellite to be here. And the satellite, we can say, has mass little m. And we want to use our forces strategy, so we should put in the xy axis. Choose an xy axis. And now let's think about what forces we have acting on our satellite. Actually, there's only one force we're considering. We're considering the force of gravity acting on the satellite. And so we'll put that in. It's attracted to Titan. And so we're ready. That's it. That's the only force. We're ready to apply Newton's second law in the x direction. And so again, using our equivalent problem, we concentrate all of Titan's mass at its own center, and we can put in the gravitational force equation. The two masses we multiply, and I do need to, let me define in my picture here, I've already used big R here, so I'll call this little r, the orbital radius of a satellite. And so we will have this r squared here. This is our gravitational force acting on the satellite. And over here, since we looked at the forces on the satellite, we have the satellite's mass and times the x component of its acceleration. Now, there's some special information that we know about the x component of the satellite's acceleration. Look at this. The satellite is moving in a circular orbit, and for any object moving in a circular path, there must be this component of acceleration towards the center of the circle, and the amount must be v squared over r. Speed, this represents the speed of our satellite, and r, what's r? R is the radius of the circular trajectory, and so in this case, that is what I call little r here. We do get a little bit of cancellation here. The mass we can divide through by the mass of the satellite. We can divide through by one of these little r's, and we can solve for the speed of the satellite. And it looks, well, similar to our escape speed result, but not exactly the same. This doesn't have that factor of root 2 here. And so we've got the speed, let's see here. We could calculate its speed. There's a little bit more information that we need here because we do want to find the period, the number of seconds for one cycle. How can we get the period into an equation? Well, we can also say that the speed of our satellite should be the distance for one cycle divided by the time for one cycle. Distance per cycle. What's the distance per cycle here? It's the circumference of that circular trajectory. That's how far it moves in one cycle. And the definition of period, the number of seconds for one cycle. So we can set these two equal to each other. Let's see if I have enough room here. And let's just stop and consider what we know and don't know here. We don't know the period. That's what we want to solve for. What about these other? We do know little r. All right, that's the radius of the circular trajectory. We do know the gravitational constant, and we do know the mass of Titan. So there's a bit of algebra involved, but at this point we've got an equation with just one unknown, so we should be able to solve for the period. And when we plug that in, we'd get answer D. Sorry, answer E.